looks like it's more or less just us, so that's fine. But what it does mean is that I would encourage you to all ask each other questions, because it's I don't have that many questions for all of you. So I think this could be a really nice, time where we listen to each other's presentations and then just ask each other questions and have a proper discussion. So really no formality at all. It's a pity that we are not at a physical conference, but there you are. We'll just do this online. So I am Lisa Ryan, and I am a professor in energy economics in University College Dublin. I'm also one of Sarah's supervisors. That's why there's 2 UCD people in this session. And I'm going to try and chair this. So the session is on wind. The running order is Diogo first, then Sarah, and then Radek. So Diogo, would you like to get started? I hope I'm saying your name right. Diogo Romeiro. Yeah.
Perfect.
And so you're going to give us a talk on the value factor. Oh, what did I do with it? The value factor of wind in Brazil. I'm really sorry, I just lost I had your paper up in front of me 1 minute ago, and now it's there. Value factor of wind generation in Brazil, evolution and prospects. Now, because we have 2 hours if we want, and there's only 3 of you, I was going to suggest if you'd like to take 25 minutes, and then we still have time to talk. We don't have to continue for 2 hours. So really, we can see how we go. But I will cut you off for 25 minutes. Put it that way. That's the maximum. And then we can have a discussion. So it's 5 past now. So Diogo, you have until 4:30 my time, at least, wherever you are.
Okay, so thank you. It's a pleasure to be here. I would like to be in Paris, but it's a pleasure to be here with you online. So my name is Diogo. I'm from the Federal University of Rio de Janeiro. I've done my PhD there, and now I work in the Getúlio Vargas Foundation, the Center for Regulation and Infrastructure Studies in Rio de Janeiro. And I will present the paper. I will share my screen here. Just one second. So could you see?
Yeah, that's good.
Hi. So, okay, I will present this paper, The Value Factor of Wind Generation in Brazil, Evolution and Prospect. It's a white paper from the AB3E, the Brazilian Association of Energy Economics, affiliated of the IAEE. And my co-authors are Edmar de Almeida and Luciano Losekann, both from the Federal University of Rio. So I will present first the theoretical points of the article, and then present the Brazilian case to discuss some of the evolution and prospect of wind generation in Brazil. So how Percebois has said in a recent book about the new landscape of power system and power sector under deep transformation. And so during the 90s, we have a market wave, a vague du marché, from cost-driven to market-driven framework. And then during the last decade, we have a green tide, from controllable fuel to variable renewable energy. In fact, in Brazil, we have historically huge generation from hydropower plants. So the variability here is historical, it's present here, and we manage this variability. But we will discuss that Brazil is also facing a deep transformation, because now we have short-term variability. We have to face a short-term variability, and the hydropower plants with reservoirs, we have to manage a long-term variability, a seasonality from this hydrological partner. So Brazil also is changing its power sector. And this variability and unpredictability of new sources impose new balancing, and so reliability and flexibility. So reliability depends more than ever on when, where, and how the generation and how the fuel and the source is installed, where is the generation at the moment of the availability of the resource, and how is the generation profile. So this cost comparison and energy balancing without value become meaningless. The traditional rule of thumb become obsolete. The levelized cost of electricity, as we have the important paper of Josko about how to compare dispatchable and non-dispatchable technologies. And so this rule of thumb, levelized cost of electricity, capacity factor, average price, grid parity, without value, without the value of without the partner generation, the value of the electricity become meaningless. So we have a kind of disorientation in how to compare resource and guide investment. This is the framework of the discussion. We have a huge literature that the international agency also having incorporating in its analysis of the marginal value of electricity and the integration cost. And we have this. This is an interesting insight from Lahon about the integration cost and a duality in two different ways. We can think the integration cost in a bottom-up version. We have the levelized cost or the system levelized cost of electricity. For example, the WEO, the World Energy Outlook from the International Agency since 2018, I think, show a system levelized cost of electricity that add value from this levelized cost, or add the integration cost from this levelized cost, and we have the system levelized cost. And or we can think in terms of top-down approach, so not to see the average price, but the weighted average price from the generation profile of the source. So the main point is that, and both of these approaches is a duality. So we can estimate this integration cost in a cost bottom-up or a top-down approach. So the point is that all sources are subject to integration costs, positive or negative, that will be a benefit for the system, and that the marginal value depends on the degree of penetration and system characteristics, and that the relation between cost and price does not determine an absolute competitiveness that we always see at the levelized cost, for example, of solar, and look to the coal and say, oh, now we have solar is more competitive than coal. We do not have an absolute competitiveness. It depends on the degree of penetration of each source in the system. So for a given price in a system and a given amount of energy from a source is competitive. And we have a huge literature about this point. And regarding this relationship between the average price and the weighted average price weighted for the generation profile, we can draw the value factor of the source. So we have some nowadays a lot of papers that estimate this value factor. For example, Lahon, Bornstein, Ishad, Shimalensi, a lot of great authors that have looked to these different countries, and the paper tried to look this calculation for wind generation in Brazil. So this value factor is a ratio between the output weighted average of the spot price and the unweighted faced by the plant. So regarding the quantity and the profile quantity, the hourly profile quantity of generation of this source, and the ratio between the unweighted average price, the average price. So looking these two different curves, the ratio between average price and weighted price, weighted by the profile generation. And this is a good indicator to calculate or to show the integration cost of the sources, this difference between the average cost and the weighted price that the source faces regarding profile generation. Just one comment: if we have a 100 capacity factor, a thermal power plant, a base load, the base load will face the average price because the generation partner will be a base load. But when we look for example, a solar panel or wind generation that face a high variability, it depends the hourly of the production. So solar is during the day. If you have a peak load during the day, it's one situation. If the peak load is during the night and your production of solar is during the day, you have another situation and another weighted price. And the big attractiveness of this approach of value factor, of the top-down approach, trying to estimate the integration cost in the ratio between prices, is that we do not need to calculate a bottom-up integration cost and the component. So we do not require the composition of integration cost, and also this dimension of this indicator of value factor we can compare over time and across systems and countries. So it's very an interesting indicator for that. And so, for example, Lahon tried to compare a hydro system and a thermal power system regarding the value factor of these different systems regarding the market share. So looking at a thermal system, the drop of the value is more quickly for a low level market share comparing the hydro system, because hydro provides a huge flexibility for the system. So the drop value in this case less for the market share. So hydro system could face a high level of variable renewable energies without facing variability problems in the system. So we have different type of effects. We have the merit order effect, that the variable renewable energy tends to reduce the unweighted average electricity price and the average price, and the cannibalization, the self-cannibalization effect, that the high penetration of variable renewables tend to reduce the marginal value of variable renewables over time regarding the weighted average price. So the integration cost is inferred by the premium or discount or the market value over an average price, the ratio of value factor. And the points that Herth raise that flexibility of hydro reservoirs mitigate the value drop of wind power in hydro system compared to thermal system. This is very important to Brazil, the case we will discuss in the next slide. And this is some papers that we have. Oh, sorry, this is in Portuguese. I forgot to translate some of this, but the main article is there. For example, Tripp and Weiser about the value of wind generation. Borenstein, the premium over the market price of solar, and a lot of other papers that estimate this value of variable renewable energy. And now we are discuss these points for the Brazilian power system. I don't know if you know if you know the Brazilian system, the main features. We have a huge interconnected system almost in the entire country, and we have a huge hydro reservoir. So we have the wind. Nowadays the hydro capacity is around 70% of the power matrix, and we have hydro reservoir mainly in the southeast region, where is located the most part of the load is here. And the wind generation is nowadays 18 gigawatts of capacity, and is located mainly in the southwest region here, and in the northwest region, and little in the south as well. So just these two regions. And we have a partner of a seasonality of wind generation. This is green bar here. And so here's the generation of the sources. In the right axis, we have the hydro generation, around 70% during the year. And this gray area is the dry season. So the wind generation occurs mainly during the dry season. And also the yellow bar is the biomass generation from sugarcane, also during the dry season. So we have a complementarity between the hydrological generation and the renewable from wind and biomass during the dry season. But when we look to the hydropower capacity of hydro reservoir regarding to the load, we are facing a decreasing of the hydro reservoir regularization capacity because we do not, we can't expand the hydro reservoirs in the last decade of new power plants with reservoirs. So the expansion was without reservoirs, and the capacity of reservoirs regarding to the load is decreasing in terms of month of reserve. So the green is the power thermal generation, the average of power thermal generation during the year. So historically above 10%, and nowadays is around 20% of the generation. And this is the blue is the maximum energy in the reservoir regarding to the annual load, and the red is the current energy stored in the hydro reservoirs regarding the year load. So the month of reserves is decreasing, and we are depleting using the hydro reservoir a lot last year. So And this is the evolution of wind capacity, the capacity factor, the blue curve, and the average generation, this gray curve, and the green is the installed capacity. Nowadays we have 18 gigawatts. So the expansion is mainly renewable and also a little of natural gas. And the natural gas depends on the dispatch. It's a flexible generation. Okay. So we look to these years of wind generation, average generation. One important information is that we have a national operator of the system, and we do not have an energy market in Brazil. The operator runs a model and calculates the operation marginal cost for 3 different load levels. And since last year, the national operator is running a model to set hourly price. But this hourly prices is it's a lot correlation with the load level. So we do not have a high granularity of prices in Brazil yet, but we are now trying to introduce more granularity. And we have 4 subsystems: the south here, the southeast and midwest here, and the northwest and the north region. And we have some constraints in transmissions line between this region, and wind is located mainly in the north region and the south. So the value factor that we calculated in the load profile wind generation, we use the operation marginal cost as a shadow price for calculate this rate. And this is the evolution of the hydro reservoirs in the northeast that account for around 70% of the total reserve of hydro reservoirs in Brazil. And here is the operational marginal cost of the region: south, southeast, and northeast. So this graph shows that the operational marginal cost is like opportunity cost of water in a hydro reservoir in Brazil, and the operational marginal cost as a shadow price. So the calculation is, we will show a little this historical seasonality of the sources, and show that when we depleted, use a lot of the hydro reservoirs, the operational marginal cost grow a lot, and this transform the relation. And here, sorry, is reais or current in megawatt hour. So this is the evolution of wind value factor in Brazil regarding all of the wind generation. And we have a premium in the northeast regarding to the south region of wind generation. And these value factors change over time because the operational marginal cost and the partner of this operational marginal cost during the year depends on the hydro reservoirs availability. So, for example, in 2015 was a dry year, and we use a lot of the hydro reservoirs, and the operational marginal cost growing a lot, and this changed the partner of the generation of the weighted of the partner generation of wind. So this is why we have a change in the value factor. This is a aggregate value factor for all wind generation. And we also calculate the capacity factor and adjusted capacity factor, for example, as Chimalense has done for United States, and has argued that it's preferable to look for adjusted capacity factor for the value factor instead of just look the capacity factor. But in Brazil, we do not have a high granularity of price, so this is in terms of region, no locational marginal price. A little different. And this is for data for some selected wind farms in Brazil. And the idea is to show that we have a seasonality. The high availability is during the dry season, between May and September, October, and during almost the great part of wind farms, the high availability is during the night, not during the day. But we have some regions of the country that the availability of wind farms during the day, the high availability. So we look from these different types of wind generation profiles to investigate some difference in the value factor. And this is some selected wind farms, and we have.
Diogo, could you begin wrapping up? About 2 more minutes.
For sure.
Thanks.
Sorry?
Let's continue, please. Continue.
Okay, 5 minutes. Oh, it's fine. I'm always there.
You have microphone off.
Oh, thank you. Sorry. So the current result there is the main result there is the current valuation only captures a long-term variability that captures a benefit of the seasonal profile of wind water availability, and do not capture a short-term variability that now we are facing with more in a common way, meaning the northeast region with a lot of variable renewable energy insertion. And also we show that this yellow wind farm here have the biggest availability during the year and a high value factor during the days, because we have three load levels, and this level was the higher level of price. So the value factor captured this, but not the contraction, the contract of these sources, because we have auction and PPAs for long-term PPAs that just look for long-term variability and seasonality and complementarity to the hydrological availability, not the daily variation. And the final remarks is that our power system is under transformation. Now we are hourly operation marginal cost, lower reliance on hydro generation. We are in this year is a very worst scenario for hydro generation. We are also discussing a critical supply circumstances and a high probability of rationing, for example. We are facing a higher risk for that this year, because we have a lower reliance on hydro generation, and We are depleting a lot the hydro reservoir. And we are facing a higher short-term variability in terms of the resources of the supply, and we do not have a properly energy market and a signal for demand response, right? So the analysis of value factor shows that wind expansion did not capture advantage of short-term variability in terms of granularity, just long-term variability, seasonality from the dry season and wet season of the hydrological production. And the idea is that the value factor can be very useful to assess current transformation and to guide a new expansion in this system. The next steps will be updated our calculation for hourly prices. In fact, we have done in this paper, I haven't showing here because it was for shadow hourly prices, but now we have really hourly prices, and we are updating this calculation, and we'll consider a large sample of wind farms with different hourly generation parts. So thank you for your attention. With pleasure present for you. Thank you.
Okay, thank you very much, Diogo. That was really interesting. I think that's a fascinating topic. It's one that's big in Europe as well at the moment. So I'll open it to the floor. Would anybody like to ask a question? If you would like to raise a question, yeah, just raise your hand, and you do that by the reactions kind of icon at the bottom of your screen. If you click on that, you'll see a raise hand button that you can press. So I would like to encourage you to ask questions. Radek, go ahead, please.
Yes, I found the raise hand. So
yeah.
Have you tried to run these estimations on like last year data, or you don't have an access for last year data?
In fact, thank you for the question. We are updating this now. In fact, this paper, we have data until the middle of last year, and we use shadow price of hourly, the shadow of hourly price, the first attempt of the national operator when we began to run the hourly prices. And now we have 1 year and a half of hourly marginal price. The big issue here is that the difference between the hourly prices and the load level is not so significant. So we will update them for the new version of the paper, but until here, we do not see a lot of difference in the result, considering the load levels or the hourly marginal price.
Correct me if I'm wrong, because as I understand, in Brazil, you have the pricing system based on like each hour end customer pays different price for for example, kilowatt of energy, and it depends on the loads?
No, in fact, the main driver is the hydro condition, because the operation marginal, the national operator system runs a model that looks for the hydro level, the demand projections, the supply projection, and calculate this operating marginal cost. But in fact, we have for the low voltage consumers, they are captive with the distributed companies that sign long-term PPAs contracts. So the signal for demand response is very low in Brazil. We are under this transformation, and also the generators sign these long-term PPAs and have just a settlement of difference between the contracted energy and the realized energy. So we do not have a spot price, we have a settlement, we have an operation marginal cost that is a shadow price of hypothetical spot price, and we have a cap on this operation marginal cost to the settlement of different in a monthly way. Right? This is our framework here.
Yeah.
I don't know. I'm seeing here Luciano Losekann is a co-author. If you want to add something, Luciano, feel free. It's a pleasure, your presence.
Thank you, Diogo. But I think your explanation was enough and it was very rich. Thank you.
Okay, thank you.
Okay. Any other questions here? I don't see any. I might just ask. I didn't understand exactly, Diogo, the trend. Why is hydro reducing and natural gas increasing over the last few years? Is that just a physical characteristic that there's less water, that there's drought, or what? Maybe I missed that. Or why are the thermal generators increasing?
Thank you, Lisa. The thermal generation was increasing last decade in Brazil because we are using a lot of hydro reservoirs, and the hydrological conditions change, and so the load grow during the years, and our hydro reservoir capacity is steadily, because the new hydro power plants were constructed without new reservoir capacity. So we are using the hydro reservoir and need to complement this hydro generation. And we have contracted a lot of thermal power plants in a flexible for flexible generation that depends on a merit order curve. So using a lot of the hydro reservoirs, we need the operation marginal cost increase, and we need a complement generation. So the national operator system that run this model and set the operation marginal cost and dispatch the thermal power plant for flexible generation. Now we are facing a problem with that because we have critical hydrological situation, and we need a lot of thermal power generation this year.
And sorry, one last question. How do your value factors compare with other countries that you calculated? Have you looked at?
Yes, our attempt is to compare this evolution and the level of the hydro and the level of the value factor. I think that it depends on the market share and the condition of the system, because if we are comparing to a capacity constrained system, the drop value of the value factor for the market share of variable renewable is very fast. And in Brazil, the problem that we face doing this calculation is that our value factor is changing regarding the hydrological conditions. For a dry year, that the operation marginal cost is very high, the value factor of wind is very low. So the big driver here is a long-term variability. And perhaps looking for the hourly prices, the recent hourly prices, we can capture some short-term variability. And also, one interesting thing is that the operation marginal cost calculates the local marginal prices for Brazil. Do not use, but they calculate. So another possibility is to look to this 70,000 location marginal price and calculate this relation regarding transmission constraint.
Okay, thank you, Diego. I think that's really interesting, but we probably should move on to the next speaker. So thank you very much for your presentation. And if anybody wants to get in touch with you afterwards, I'm sure you can find him via the program. So next we have Sarah Stanley, who is a PhD researcher in University College Dublin in Ireland. And she is with the School of Electrical Engineering and also partly in the School of Economics. And before her PhD, she was an analyst in the National Energy Agency in Ireland, SEAI. So Sarah is going to talk about is the transition to zero carbon power economically feasible, the case of a 70% variable renewables power system. So Sarah, would you like to share your screen?
Yeah, thanks, Lisa. Okay, how does that look? Do you see the first slide? Yeah.
That's fine, yeah, go ahead. And so again,
Okay.
sorry, Sarah, you can take 20, 25 minutes as well.
Okay, I'll see how I go. Thank you. All right, thanks for the introduction, Lisa. As you said, I'm a PhD student in University College Dublin's Energy Institute. And my research is funded by the Department of Environment, Climate and Communications in Ireland. And I'm going to be discussing the operational and financial challenges beyond 70% variable renewables, using Ireland as a case study. So in the presentation, I'm going to briefly give you a context for my research. I'll talk you through the methodology that I've used. I'll introduce you to Ireland and its characteristics. Then I'll talk through the portfolios that we've used. So I'm looking at the year 2030, so the portfolios that we've got for 2030 and the operational constraints that we've put in the model. Then the rest of the presentation will be the results from the model in terms of generation and prices for different technologies that we're seeing in 2030, some financial analysis we've undertaken, and some sensitivity analysis, including the impact of price responsive or smart heat demand. And I'll finish with some concluding remarks. So in terms of the context, as we all know, there's rapid changes in the power sector with increasingly ambitious decarbonisation targets. In Ireland, for instance, we had a 40% renewable electricity target for 2020, which we have approximately met. For 2030, the 2019 Climate Action Plan aimed for a 70% renewable electricity share, and that's likely to increase this year. So in countries without significant hydro resources, we're looking at a very high share of variable renewable electricity from either onshore or offshore wind and solar photovoltaic. In order to ensure operational security, variable renewable electricity will require additional flexibility, reserves, interconnection, and storage. However, there's a question mark over the existing market mechanisms and whether they're fit for purpose with a high share of very low short-run marginal cost renewables. So we use a unit commitment model to test scenarios in the quite extreme isolated system of Ireland. So the methodology that we've used, we have a unit commitment and economic dispatch model called Backbone. Backbone was first developed in Finland by VTT for the Nordic power system. And it's since been adapted by ECD in conjunction with VTT to the Irish system. It's quite a complex model with a range of potential applications. So you can see here the objective function. If you include data for investment, for the parameters in green, it can be used over a long time horizon for investment modeling. Similarly, it can be used as a stochastic model if you use the probability function. But in our case, we've used it as a scheduling model. So that's short term, looking at the year 2030, but at greater granularity. So at 1 hour intervals, and that allows us to have quite detailed operational and unit specific constraints. So in terms of, this is an overall schematic of the backbone model. You can see that different energy types can be included. We focused on the electricity grid. You have different nodes within the circles in the schematic, and in these nodes you have individual units. So for instance, you could have a gas thermal plant that is using gas from the gas grid and transferring that into electricity at a certain efficiency or heat rate, and that's going into a node in the electricity grid. So nodes are connected within the grids by lines, and they transfer energy of the same type. So for Ireland, we've built an all-island node for the single electricity market in Ireland, which includes the Republic of Ireland and Northern Ireland. So you can see a map of Ireland there. It's an island on the west coast of Europe. It's to the west of Great Britain, and it's connected at the moment to Great Britain by 2 interconnectors. By 2030, there's an expectation that there'll be 2 additional interconnectors, one more to Great Britain and another to France. So we will be rejoining the European electricity market through the interconnector to France post 2023. In 2030, the Irish target is, as I said, to reach at least 70% renewable electricity. And it's likely that the majority of this is going to come from either onshore or offshore wind. In addition to renewables, the model has 70 generation units, approximately 70 generation units in Ireland, and that's primarily from gas. And so we have combined cycle gas turbines and open cycle gas turbines as for peaking plants. Then we also have some biomass and some hydro units. We've also included primary and tertiary reserve, as well as battery and pumped hydro storage for 2030. The portfolios that we've used for 2030 are based on the transmission system operator scenarios. Both of them meet the 70% renewable electricity target. However, the high scenario is slightly more ambitious in that it has a higher installed capacity of renewables, in particular onshore wind and solar. It also has higher ambitions for electric vehicle uptake and heat pumps. The central scenario also meets the 70% target, but is more focused on offshore wind and has a lower share of electrification of heat and transport. So in terms of the operational constraints, Ireland has broken ground by recently reaching 70% system non-synchronous penetration. And what that means in practice is that up to 70% at any time of demand and exports in Ireland can be met by non-synchronous wind and solar and imports. So to reach our 2030 targets, that's going to have to increase to 90%, and that introduces a number of challenges. High variable renewable electricity removes the stabilizing rotational inertia that is provided by conventional generation plants. On top of that, in Ireland, a single infeed or generator can make up a large share of generation. So for instance, 20% of total generation can come from a single source or a single generator. Reserves, Ireland has quite rigorous reserve requirements to ensure that there's capacity available within different timeframes. So it can be a few seconds to a few minutes to restore any imbalance from demand and supply. And we've also included a rate of change of frequency limit of 1 Hertz per second in 2030, which implies a minimum inertia constraint in the model for operational security. So demand in 2030, we have 2015 demand in yellow. Then on top of that, we've included space heat demand from heat pumps in orange, then electric vehicles in blue, and also data centers there's expected to be a significant amount of data centers in Ireland by 2030, so much so that they're going to make up around 30% of demand in that year. So the rest of the presentation is going to be the results from the model. So just to recap, we ran two scenarios: a central and high renewable electricity installed capacity and electrification of vehicles and heat scenarios. Both are run with operational constraints to get results for generation, and they're run without operational constraints to get an estimate for marginal prices in an energy-only market. We've also included some sensitivity analysis with a share of smart heat demand. This is going to provide insights into the generation mix and the impact of operational constraints on generation, and also into the prices that different technologies are going to receive and the unit revenues that they can expect in an energy-only market. So this is a snapshot from 2030. It's taken from February, the week in February. And I chose this week because I think it illustrates quite well what happens when there's low wind power on day 2 and 3, low wind and solar. And then that picks up during the week by day 5. So it picks up so much so that it goes beyond the load in Ireland. So I think it goes from around 1 gigawatt to 8.5 gigawatts in a day, or less than a day. So what you can see here is that when there's low wind and solar, demand is being met by CCGT plants, OCGT, and imports. Then as renewables pick up during the week, wind can theoretically meet the load, but to ensure operational security, you see that there's still some CCGT online, as well as some hydro in green. So what we'd expect in terms of prices is as renewables start to meet the load, the full load, that they'll drop towards zero since they have a short-run marginal cost of zero. And that's what happens. You can see on day 2 and 3, prices are peaking as a result of relying on more expensive peaking plants to meet demand. And then on day 5 and 6, the price starts to fall to zero. Then looking at international trade on the interconnectors, you can see here the imports from Great Britain in orange, which are positive, and you can see on day 2 and 3 that we're importing from maximum capacity from France in particular, since there's an assumption that the electricity price is going to be slightly lower in mainland Europe than in Great Britain. So we're exporting or importing at maximum capacity when our prices are very high in Ireland, and then we're also importing from Great Britain. Then on day 5 and 6, we start to export at maximum capacity to Great Britain and France, when the assumption is that the prices are going to be greater, at least greater than zero in both of those countries at the time. So this is what's happening with batteries for this week. So you can see there's reserves provided from batteries, as well as a source of storage and generation. So batteries are storing power when electricity prices are low, and then releasing power. So they're when electricity prices are high. So they're also acting as a source of flexibility for the grid. So we have undertaken a bit of financial analysis as well, using the market value factor and net present value. It's slightly different from slightly different methodology from the previous presentation, but we have looked at the value. So as you spoke about before, the value of electricity is based on the price at the time of sales, since electricity prices change hourly or throughout the day. So what you're looking at here is the market value factor, where the price that a technology is receiving compared to the average price in the market. So if the market value factor is less than 1, for instance, on average, a technology is receiving a price that is lower than the average price in the market. We've also calculated the net present value. So that's cash flows discounted to today's prices, using discount rates from Grant Thornton's industry survey, and assuming that they're going to stay the same in 2030. And we also have different discount rates for different technologies. And then you minus the initial capital investment to get final net present value. So first of all, just looking at the market value factor in 2030, you can see here that for wind, wind has a market value factor of 0.8 in the central scenario. And this is due to the fact that it's non-dispatchable. So there is a mismatch with electricity demand naturally. And it's also due to the fact that wind penetration will lead to periods of zero prices, very high wind penetration. In the high scenario, the market value factor for wind falls to 0.7. And this is a result also of a higher level of curtailment in the high scenario. So there's a share of wind that is being curtailed, or excess wind that is being wasted and not finding a route to the market. With solar power, solar in the central scenario has a market value factor of 1.1. So this is indicating that solar power is being sold during the daytime when on average prices are slightly higher. In the high scenario, due to some additional curtailment of solar with a higher installed capacity of solar in the high scenario, that market value factor falls to 1. In studies that have looked at a very high level of installed capacity of solar, the MVF can fall to as low as 0.4. However, this is less of an issue with wind since it's more distributed across 24 hours. You can see here that OCGTs by far have the highest market value factor since they're selling their electricity during periods of scarcity. So in the high scenario, these are quite regular, and the market value factor reaches up to 4.4. So in terms of net present value, we've made this simplifying assumption that different technologies are receiving the same price for the entire length of their project. So that's the price in 2030. And based on this, wind in the central scenario is expected to make a profit. So when you're interpreting the net present value, if it's positive, then the project should go ahead, it should be profitable. And if it's negative, then it's expected to lose money overall. So in the central scenario, wind is profitable. But it's in the high scenario when there's higher curtailment of wind that you're looking at wind requiring other sources of funding to be profitable. With utility solar, the main difference is the investment costs. So projected investment costs for utility solar are quite different in terms of the low and high investment cost. So in the high scenario, utility solar would have a negative net present value. OCGT will require other sources of funding, either from capacity markets or from reserve tariffs or system service tariffs. And biomass is on the line primarily because it has a higher discount rate than other technologies, even though it has a high load factor and is providing electricity for most of the year. So this is a sensitivity analysis that we did, including some price response of heat demand. So by 2030, we're assuming that around a quarter of residential homes have an air source heat pump or a heat pump installed. And if we make the simplifying assumption that 50% of these homes have the option of either switching to gas or are installed with a storage tank so they can use stored heat during periods of very high electricity prices. And this is what happens. You can see that the load shifting takes the pressure off prices. And so this is going back to that week that I showed you before. It takes the pressure off prices on day 2 and 3. You don't have the same peaking occurring. And at the same time, it's absorbing more excess electricity produced by very high shares of renewables at certain periods during the year, which you can see on day 5 and 6. And so just looking at those renewables, you can see for the net present value, it's more likely that these types of technologies would be able to survive in an energy-only market with higher demand shifting. So just to conclude, renewable electricity in Ireland can at times greatly exceed the load. So there's instances in 2030 when variable renewables are 3 times the size of the load. So there's a role for demand shaping and storage. There's existing barriers to implementation, particularly with demand shaping, that still need to be addressed, such as smart meter rollout, aggregators engaging participation, and data protection. Profitability of conventional generation and storage is also very important. In Ireland, the importance of capacity markets and tariffs for system services and reserve to incentivize investment is something that we're going to look into a bit deeper next. Okay, thank you very much. That's the end of my presentation.
Thanks a lot, Ciara. Very interesting and comprehensive. So I'll open the floor now to the panel who would like to ask a question, or do you have any thoughts or comments on the work? I think it's interesting that you're also looking at the value factor, which is nice follow on.
Yeah, it was, but I noticed there that we have a slightly different methodology, and I saw that there was different ways that people had used the value factor, so I thought it was interesting.
Yeah, something to go back and look at, maybe to compare the results. Yeah.
I have one question. Congratulations for the presentation. Can I make it now?
Yeah, please go ahead.
Okay. Do you, in the final remarks, do you point the need of a capacity market for attracting new investment?
Yeah.
But you also show that we have a high value factor for some for dispatchable sources. So how do you think about this two? If you estimate a high value factor, probably the missing money in the energy market will be lower, and you need perhaps you don't need a capacity market for these sources. How do you see this link between these two things?
Yeah. Yeah, no, that's a good question. Like, so the high value factor in terms of the conventional gas plants is due to these plants receiving a very high price at certain periods during the year, but then for the rest of the year they might be running, so that's not going to cover their overall costs. Looking at net present value, so that's where the capacity markets will come in. The prices alone wouldn't cover the total costs, including the capital investment and long-term costs.
Do you have already a capacity?
So there is a capacity market, huh?
Sorry, do you have already a capacity market in Ireland?
So we have a capacity market in Ireland already, yeah, and that's something we're going to look at next, is looking at the revenue that generators are receiving from the capacity auction. So it's been changed recently to an auction system. So it'll be interesting to see, but we haven't done the analysis yet. Because yeah, there's a with the higher renewables in Ireland, there's a need for a more flexible plant. So yeah, it's very important to ensure that the investment incentives are there.
Yeah.
Thanks.
Ciara, if I can ask a question, I think it's interesting that the well, the NPV results are, you know, in terms of, say, ranking technologies, if you're an investor, the NPV results are quite different to the market value factor results. Which do you think the market pays more attention to? I mean, I guess the NPV allows you to reflect the total revenue coming in, whereas the MVF, like for example, solar doesn't run a lot of the time, but when it does run, it is slightly better than wind. But overall, in terms of profit, I imagine it's lower just because it doesn't run very often. Is that so? Is it MPV more that you think the criterion that would be used by industry?
Yeah, well, that's it. I would say that the NPV would be more relevant because the market value factor isn't taking into account the load factor, like you mentioned. So it's not looking at the amount of times during the year that they're receiving that price.
Yeah. And actually, the question on solar, like if I look at the plans in Ireland, they're talking about up to 5 gigawatts of solar on the system for 2030. I can't remember what the high renewable scenario that you have, like putting more and more solar installed capacity on, does that really change much? Is it running so little that it actually doesn't really change very much, or does it make a difference, do you think?
Well, the central and the high scenarios that we ran already have different gigawatt installed capacities. And you can see when you increase the installed capacity of a certain technology that in the system, there's going to be additional curtailment. And that's where the real risk is in terms of profitability in the Irish system. If they can't get curtailment down and there's not a market for the renewable power, then they'll lose out.
Yeah. It is an interesting one, I think. And just one thing on the imports, I suppose, does the model always assume that the imports flow from low price to high price? So effectively, they're always efficiently run. It's not like real life where sometimes imports run in the wrong direction, right? Everything always runs efficiently. Yeah, okay.
Assuming the market is working.
The market is working, yes. Well, that's the great thing about models, isn't it? I don't want to hog all the questions here. Does anybody else have one? I could go all day.
Well, I have maybe not a question, but I'm like interested because you have both countries, like in Brazil and Ireland, you have, it seems, much more advanced pricing system of energy than Poland, because we have still here the fixed prices that are set by the governmental agency. And there are like only, you have only like values for day, night, or like one constant, which one constant value for like households is more profitable than this one set day and night. It's called day and night because it's based on loads. So maybe someday we will be there where you are now, but we are really far from that.
Is it just, it's still
are you going to be joining?
One more time.
Go, Sarah.
Sorry. I was going to say, are you going to be joining the European target model? Are you going to have a day-ahead market for the wholesale electricity price, or? Well, that's the system that Ireland has just in the past couple of years.
Well, we supposed to, because there are a few policies of the European Union that have been taken, because we are part of this trade scheme of energy between different countries in the European Union, which saved us like 2 weeks ago, because we have like the biggest one, or like the second biggest one, coal energy plant in Europe, and it shut down because of an emergency last week. So the prices on energy market, international market, skyrocketed like 2 weeks ago, and it was because of Poland. That's the one thing. And we're supposed to open our prices, I think, 2 years ago for the free market. But because our grid system is very underinvested, the government decided that we should stay on a fixed one still.
Let's see. So it's a vertically integrated model, probably still, is it, for the utilities? Yeah. So you have to liberalize as well as join the market. So there's still a bit to do, I imagine.
Yeah, but our government says that we have a coal, so we are safe.
Ah, safe for now.
Yeah.
Yeah. Okay. Well, I think thank you, Sarah. I think we'll wrap that up. This second speaker, unless anybody has anything else. I think we will move on to Radek for the third presentation. So Radosław Ślosarski, I hope I've said that correctly, is a PhD researcher as well in Gdansk University in the Department of Economic Science. And I have your presentation is going to be on, oh dear, I've put it somewhere again. I keep doing this.
But I can share my screen. So.
Okay, I have it here. Environmental effect of production of energy prices and innovativeness, the role of onshore wind energy in the top 5 contributors in to the EU economy. So over to you, Radek.
Okay.
Thank you, Ciara.
Okay. Can you see it?
Yeah, that looks good. Thank you.
Okay, so I have to remind myself what I'm gonna talk about, because last presentations were very interesting and I forgot almost everything. So first of all, I am, as you said, the PhD candidate at Gdansk University of Technology. My major is, well, my PhD studies are about mainly energy transitions and their macroeconomic implications. And here, this research is like preliminary research, or like a poll for the future research that will take into account much larger group of much larger sample. This research focused mainly on innovativeness, or like innovations, and its role in decreasing the negative impact of humans on the environment. And main purpose of this research was to research and to investigate whether innovation in energy sector, and especially the spendings on R&D in energy sector, are influencing at any way the greenhouse gas emission, because there are various publications which support the thesis that yes, they do. However, focusing on cost of technology, decreasing cost of technology by the research and development, or on the other hand, by learning by researching. So in the end, decreasing the cost of production or the installation of new energy sources, or new power capacities. So about my methodology and sample, first data. I've used the data from various databases, starting from International Energy Agency, OECD, even the World Bank, looking for the largest sample possible. I have focused first on 5 countries that are the majority of the European Union economy. They are responsible for almost 70% of the European Union GDP, and also they are the biggest producers of energy sourced from renewable energy. They are representing almost 61% of production of energy from renewables. However, at the point when I was writing this research and this article and running the estimations, I had available only data for 28 years, because for previous period there was a lot of missing ones. I've used 4 different methods just to check the main goal of this research. First, I focus on time trends to check whether the energy systems of those countries are changing at all. Second, I have estimated the Goddard learning curves that shows the relations between R&D and R&D stock and the wind energy capacity. And the second one will show the relation between the research and development stock and the knowledge stock and the levelized cost of energy, of the wind energy. The third method was running the co-integration test for various different variables and their influence, or like whether they are co-integrated with emission of CO2, because in this research I'm measuring the greenhouse gas emissions by emissions of carbon dioxide. And the third one, the fourth method was running the estimation of GMM, so general method of moment estimation. My first approach was to run the simple OLS regression. However, after a lot of reading and review of a lot of articles, I have found that I may have problem with endogeneity in my sample. And also there is some research that suggests that the value of CO2 emission, the amount, may be a result or influenced by its previous values. So, for example, the value of CO2 emitted in 2018 may be result of the emission in 2017. And running the GMM estimation allowed me to solve that problems or take them into account. So first, I looked into energy mix in this sample and how it was changing. Interesting is that during this period, as you can see, the renewables became a much larger part of the energy mix within those countries. And at the same time, the renewable energy, the energy supplied to the system and consumed increased only by approximately 5% between 1990 and 2018. What is important is that between 2005 and 2006, we had the peak of use of energy. And since then, the energy needed for the operation of countries decreased by 11%, yes, 11.1%. So as our yesterday keynote speaker, one of them said that the goal, to achieve a sustainability goal of the economy, it is important not only to increase the renewables into our energy mix. It's also important to increase the efficiency of our economies. So as you can see, the energy efficiency, it's in all of those countries from my sample has increased, and it increased a lot because it was between 1990 and 2018. The lowest increase was in Italy, where the efficiency rose by 220%, and the highest increase we could observe in Germany, where the efficiency rose by over 300%. And those efficiency is showed like the GDP per generated per 1 kiloton of oil equivalent within those countries. And okay, now looking at learning curves, as you can see, the relation between the real data, which are shown on scatter, and the learning curve, which is the red line, the increase is fairly linear. However, the first stage of the investment in R&D does not provide the huge increase in the wind production capacity. The values that you can observe here are the values that were invested by certain countries later. So they've used the convergency effect, so the catch-up effect. And something different can be observed from the second learning curve, which shows the relation between knowledge stock and levelized cost of energy. So investments in renewables provide a huge difference in a huge decrease in prices of energy sourced from the wind. What's more, looking only on the slope of this learning curve, it seems that there is a huge space for further investment that can decrease further the prices of energy, decrease the price of energy sourced from the wind. Okay, next I went to the co-integration test. I've tried to take the co-integration between the most important variables for this research objective. So the industry, value added of industry to the GDP, wind capacity for those countries, levelized cost of energy, and the RDR spendings, research and development spendings on renewable energy within those countries. And I have run the Western co-integration tests only because it's not the most popular. However, it takes into account that there may be cross-sectional dependence among the sample. This next econometrical problem that can be found in the literature and also into macroeconomic data. However, this test shows and presented that those data are correlated among whole panel, co-integrated among whole panel, and also amongst at least one individual panel sample or group, which means there is a causal relation between those variables and the CO2 emission. And finally, I run the GMM estimation, which has been later proven by the Hansen tests for over identification and Orlando bond values. What is important in this test is that as the wind capacity, which I predicted will be influential on the CO2 emission, it is fairly significant. Also, the prices of energy sourced from the levelized cost of energy sourced from the wind is also important. However, the RDR seems not to be significant, at least in this model. And also the industry is not significant. That's why we cannot, by this model, interpret whether the CO2 emissions are effect of the industrialization or not. What is also important, it seems that CO2 emissions are not impacted by its previous year values. And going to conclusion, emissions of CO2 are influenced by the capacity of the wind energy and their levelized costs of energy. And the innovation resulting from spendings on R&D is not directly influencing the amount of CO2 emitted to the atmosphere. However, as the learning curve showed, there may be relation, but indirect one, and it's needed further investigation. CO2 emissions are not influenced by its former emissions, as I said. Weakness of this research at this point is the small sample. However, as I said, it's a preliminary research, and in future, probably in a few months, I will run it on much larger scale, and mainly to see whether there is a difference, for example, between Western and Eastern Europe. And at this point, I believe there will be. And also for the convergency effect, whether it's case only of, for example, here wind, or it will also be revealed in case of solar. And thank you.
Thank you very much, Radek. That's great. So, any questions, anybody? I'll open it out to everybody else first. You can just turn on your mics or put up your hand. I don't mind. And Ronnie, could you just remind me the size of your sample? Like how many observations? Is it just annual observations for 5 countries over?
Yes, at this point, yes, because I was focusing on
years?
macroeconomic 28 years. Now
Okay.
I have data for almost 30 years, because the problem is if you are looking at macroeconomic data and scales, most countries are providing data for yearly ones, annual data. And that's a little bit problematic. However, increasing the sample for more countries that economies are much more diversified should wipe out this negative aspect of macroeconomic research.
Well, it's a proper panel data set, so you'll have all the problems associated with that. Yeah, sorry, Diogo, you have your hand up. I'll stop for a bit.
Thank you. So, congratulations. Sorry if I missed, but what is the criteria for selecting the country? The energy policy, the transition, the challenge of energy transition?
At this point, I have focused only on these 5 countries because they are the most representative for the European Union because of their influence of the economy. And I wanted to set the parameters for future research that will be run on the panel of, I would like to go for at least 100 countries, depending on the data availability. Because that's a crucial role here, because I have to see whether those data that are available for each country if they are complete, because there is a problem with those macroeconomic data that, for example, some countries can give you a 1 or 2 year break in the middle of the panel. So then I have option or to try to find it in a different database, which may be problematic because most of the data are sourced from the governmental agencies. Or the second option is to use the statistical methods just to create those data, which I really don't like to do. Or the third one is even worse, to decrease the period that I can investigate.
Okay. And how do you think to treat some changes in the energy policy? For example, in the Germany, the ban of nuclear or something like that.
Individual policies, I don't think that should, for this exact model, that there should be any problem, because here I'm investigating mostly the spendings. So like transfer more from, not from the nuclears, but rather move from fossil fuels to renewables. And I would say that the trend for most of the countries right now, each country has different pace. For example, Poland is very far away, or Germany is much further up front, but that's something that may be interesting for the results.
Sure.
Yeah.
Thank you.
Radek, I wasn't sure what the variable knowledge stock meant. That's investment in R&D or something, is it?
Yes, it's cumulative investment value from R&D.
Where do you find this data? Is this published by the OECD or somebody?
International Energy Agency.
Okay. That's interesting.
But it's available through iLibrary of OECD.
Yeah. That's interesting.
It's called in literature, it's called knowledge stock, especially concerning the learning curves. So
yeah. I mean, going back to Diogo's point with regard to policy, it's true that many models like this, they would include maybe a dummy variable for a policy change to if there's a big thing. or you might include fixed effects to take account of differences, structural differences between the countries that don't change much over time.
I think that fixed effects may be here more appropriate, because at some point creating so many dummies may impact too much the whole panel of the research. So I bet fixed effects might be better here, but yeah, I was thinking about doing fixed effects, but I had this problem with, I thought that I might have problem with endogeneity and other econometrical ones. That's why I went for the GMM estimation. Also because my 2 papers that are here now in second review involves cases reviewers had a problem with fixed effects, and all of them now say go to GMM or go to some other 2-step regressions.
Yeah, I was going to say that with the lagged variable, it looks to me like you need to have 2-step or some kind of instruments, because you must have some sort of multicollinearity, when you have the lagged variable in a panel data set, especially when you have more countries and you have a bigger time series. I think,
yes, I think I will go also to SLS, so the 2-step one.
Yeah.
Where I'm gonna just identify the wind capacity for the countries as a regression of the R&D spent on it and the cost of energy there, because that may be also some way.
Yeah,
but
although wind capacity, I don't know, in Ireland we have a lot of wind capacity, but we don't have much R&D because our turbines all come from Denmark. So I'm not sure if they're always related.
Well, we have, I'm not sure how in Poland, because we had this problem in Poland that before 2015 there was a big boom for investing in wind turbines. Even the farmers were putting on their fields the wind turbines, and the new government came, and in 2016, for some reason they decided that you cannot operate wind turbines if they are closer than 1.5 kilometers from the house, or something like that, which killed significant part of the wind turbines in Poland. So that's the way. But as far as I understand, a lot of countries are spending money on research and development in field of energy, different energies. And because it's cumulative number, that seems high, because in the end it resulted with, for this whole sample, as far as I remember, it was 2.7 billion of euros during these 30 years of investment in it. So if you look at it per country, those values are not that high at the end.
Yeah, I know this R&D data set actually in the IAEA. It is it's mixed, I would say, in terms of its quality. Yeah. But I wanted to ask you one thing: the CO2 emissions, your dependent variable, is that the total CO2 emissions for a country, or is it just from electricity?
This one is from energy.
From energy.
Yeah, from energy.
I mean, if you could get just electricity, it might be better. It would be better because it's more direct.
For this sample, I could, because I know there it exists. I'm not sure for the target sample of large ones, panels. Yeah, but I will see that when I get there, because that will be a lot of playing with data and econometry, which I'm not the biggest fan, but well.
Yeah, no, I think it's an interesting project. I mean, there are some literature I'm sure you're familiar already with in this area, looking at the the causality between renewable electricity and CO2 emissions.
There are some, but in many cases they are on very small sample, like even 2 or 3 countries, so mainly case studies rather than macroeconomic approach. Yeah.
And the energy efficiency part, how will you include that? I don't think it's in your econometric part at the moment, is it?
The efficiency, it is. It was important.
Oh, it is included.
Yeah, it is included. It was important. However, it was used as a support data. It's called stuff like that. So it was not the most important for the analysis here. But to be honest, I could predict before that model that efficiency is important, because I'm including and working on a few other researches that include efficiency. One, for example, on the question whether European Union's energy sector is in transition or just evolving. So their efficiency was also very important there.
Yeah, I mean, the thing is that the number that you have GDP per ton of oil equivalent, that's really energy intensity rather than efficiency. I mean, efficiency is more a relative concept. So like there will be quite big differences in terms of structure. So I just wonder what you're measuring. Are you interested in measuring the change? Is it a percentage that you should include in year-on-year change? Or is the right value the absolute like levels in terms of GDP per ton of oil equivalent? A fixed effect might capture a lot of that, actually.
Yeah, that's a good question, because this is like, I really like this measurement where I can see like how much GDP, because it's like it's not a substitute, but it shows similar thing as the GDP per capita. So the amount what I showed here, and I really like it because it's clear for everyone that reads it. Yeah. And at some point, especially in statistics and econometrics, and a lot of research can be so vague that at the end, I'm not sure what I'm reading. So I'm trying to simplify as much as I can.
Yeah. Yeah, it's just a little bit controversial is what I would say, because it's not really reflecting energy efficiency investment. You know, it could be just that you have a services industry in one country and you have a more heavy industry in another country, you know, so it's like in the IAEA, they decompose this value into structure, activity, and efficiency. But it's very difficult to do that, so I don't know.
Yeah, but also in this case, the industry should show, if that would be a case, I think that industry variable of the industry should be important, or should be significant for the model if that was the case in here.
Yeah, it should, I suppose. Yeah, in terms of, it could be quite correlated actually, if anything. Yeah.
Yes.
Yeah. Anyway, sorry, I'm going back and forth with you here. Does anybody else want to say anything? I do enjoy this discussion. No, I think it's just us that's left in this session. So. And then I won't keep you. I've really enjoyed the presentations and meeting you all today. So I think we might as well finish. There's no point continuing unless anybody wants to say anything. We have Jean to thank, our session host, who has kept everything running smoothly.
Thanks.
Thank you very much.
Thank you a lot.
So then I will say thank you to you all. Thanks to all the speakers. And I enjoyed your papers. And yeah, I'll follow them with interest as they develop. Thank you very much.
Thank you very much.
Pleasure.
Thank you. Bye.
Bye, everybody.
Bye.
Bye-bye.